Good morning, everybody. This morning we're going to start a new unit, uh, leaving acyl substitution behind for the moment anyway, and now progressing to a new family of reactions dealing with the proteins and the amino acids. Also want to remind you that we have an exam next Friday, and we'll probably do it logistically the way we did the exam we had a couple of weeks ago. And so I think maybe try to finish up the material for the exam on Friday's lecture, and I'll publish a study guide. So it'll be a similar run through of what we had for the exam a couple of weeks ago. All right, so I want to talk about the amino acids and the proteins. First of all, so let's see. The alpha amino acids. These are the building blocks of proteins. And also the enzymes, right? Because enzymes are a special type of protein. And when we get into protein, maybe next week or maybe it started on Friday, we'll go through where in the physiological system proteins are encountered. It turns out that it's not just something that we have for dinner. And we've talked a lot about enzymes, and enzymes are proteins as well. So the alpha amino acids, these are the building blocks of proteins and of amino acids. Okay, so now let's talk about this terminology here, the alpha amino acid. So the alpha amino acid is a special type of carboxylic acid. There's the carboxylic acid carbon. The carbon next to the carboxylic acid carbon, that is called the alpha carbon. An alpha amino acid is a carboxylic acid that has the amino group at the alpha carbon. So for right now, I'm going to make a huge deal out of what's going on with this nitrogen atom in a minute. But just for right now, just to keep things simple, but not 100% correct, we'll just put this amino group on the alpha carbon. So this is what an alpha amino acid looks like. Now there are, if you know the Greek alphabet, you know that the letter after alpha is beta, and then gamma, and then delta. Well, there are also those types of amino acids, but this alpha amino acid, these are the alpha amino acids that are coded for by DNA. So the alpha amino acids, these are coded for by DNA. So you know about DNA, right? And how DNA is a template for the manufacture in a physiological system of proteins, and proteins are made out of amino acids. So the alpha amino acids, and not the beta or the gamma or any other kind of amino acid, that's what DNA is there for, to create the sequence of alpha amino acids in a protein. Okay, so speaking about DNA, this alpha carbon is going to have a substituent on it, and there's nearly all the time, there are some exceptions, going to also have a hydrogen on it. Okay, so this R group here can be about, there's about 20 different groups. So R could be a hydrogen, it could be a methyl, it could be a bunch of other substituents. There are about 20 different groups coded for. by DNA. And these were coded for by DNA. And these are the so-called proteinaceous alpha amino acids. They're the alpha amino acids that we find in protein. So when we're talking about alpha amino acids, we're talking about a carboxylic acid that has the amino group on the alpha carbon. What's the alpha carbon? The alpha carbon is the carbon next to the carboxylic acid carbon. And this alpha carbon can be substituted by about 20 different groups. Okay, so that's what an alpha amino acid is. So let me introduce you, or try to introduce you now to your new BFF. Wow, you've made a lot of friends in this class. So I'm going to try to share my screen. What am I want to share? I want to share this one. Okay, so on the course website, in the lecture entitled Amino Acids, I have this chart here. And so this chart is, we want to get to know, want to be able to use this chart and be able to interpret the information that it is telling us. So this is on the course website, and so you don't have to memorize any of the information here, but you do need to know how to work with this chart and what information this chart is telling you. Okay, so there are 20 amino acids, proteinaceous amino acids. How many are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yep. So these are the 20 amino acids that DNA codes for. Each amino acid has a 3-letter abbreviation. So alanine, for example, is abbreviated ALA. Glycine, for example, is abbreviated GLY, and so forth. So this is the, oh, it's chalk. This is the older system of abbreviation of the amino acids. There's also a 1-letter abbreviation of an amino acid, which is, saves a lot of time when you're typing this at a keyboard of a computer. But I'm not going to get into that. I do want you to realize, though, that there are 2 systems for designating the amino acid, a 3-letter system and a 1-letter system. I'm going to concentrate on the 3-letter system because the 1-letter system frequently has nothing to do with the name of the amino acid in the English language. So for example, lysine, the 3-letter abbreviation is LYS. Oh, makes sense, right? Lysine is LYS, INE, the 3-letter abbreviation is LYS. The 1-letter abbreviation is K, right? Which makes absolutely no sense to me, but that's what it is. Okay, so I just want you to realize there's a 1-letter abbreviation, there's a 3-letter abbreviation. We'll be using the 3-letter abbreviation. Okay, so the amino acid is a carboxylic acid. And so what these pKa values that we're going to get into in a minute, these pKa values, they're telling you the pKa of the carboxylic acid proton. The amino acid has an amino substituent at the alpha carbon. And that amino substituent is also associated with pKa values. And so this next column here is telling you what the pKa of the amino group is, right? Remember I said that the alpha carbon can be substituted with any of 20 different groups of the 20 proteinaceous amino acids that are coded for by DNA. So this entry here, side, is telling you what the pKa of that R group on the alpha carbon is if it has an acidic substituent. Not all of them do. Finally, this last column is telling you what the side chain is. This is telling you what the R group is on the alpha carbon. For alanine, the R group is a methyl group. So for serine, the R group is a CH2OH group, and so on. So these are the groups that are on the alpha carbon. All right, so we're going to make extensive use of this table, so please become familiar with it. Whoops. Oh dear. Speaker view. Okay. So that table I just showed you, it has all of the, when it talks about the side chain, what it's talking about is the identity of these various R groups. All right, so let's talk about some glittering generalities about the alpha amino acids. So a lot of you folks are interested in biochemistry, you're interested in nutrition, and you're interested in dietetics. Well, one of the things that we know about, one of the classifications of the alpha amino acids is that some alpha amino acids can be synthesized by your body. We've talked about examples of this. If you look back at the lecture notes dealing with the imine and tautomerization, I went through how, for example, the amino acid alanine can be created from pyruvic acid, which is not an amino acid. So there are some amino acids that can be synthesized by the body, but there are other amino acids that must be consumed in the diet. So these are the so-called essential amino acids. These are the essential amino acids. And what we mean by essential is they must be supplied by the diet, because your body can't make them. And if you don't eat enough of these amino acids, then you're going to get a deficiency. Okay, and so the essential amino acids, you don't have to memorize this, right? I'm just telling you because I think a lot of you folks are interested in biochemistry, dietetics, and nutrition. So that's why I'm mentioning this at this point. Okay, so the essential amino acids are histidine. I'm writing the three-letter abbreviation. Isoleucine, leucine, lysine, methionine, phenylalanine, threonine, tryptophan, and valine. Okay, so these are the amino acids that must be supplied by the diet. Not all of these amino acids, and remember there are about 20 proteinaceous ones, they don't occur in protein in equal amounts. Some amino acids are quite common, other amino acids are very rare. Okay, so what I want to do now is to show you what the most abundant amino acids are and in protein, and what would be the rarest amino acids in protein. So abundance. The most, yeah, I'm just going to erase this. I'm going to need a lot of reals here. The most common amino acids. This would be glycine, about 11% of protein is glycine. And I haven't memorized the structures of all of these amino acids. I know a lot of them, but I don't really know all of them. But I know this one. So glycine is just this. And remember, there's the alpha carbon. The alpha carbon will nearly always have a hydrogen there and some other group, right? And so glycine just has this hydrogen here. So its R group is hydrogen. That's the most abundant. That's the most abundant amino acid, about 11%. And then we have alanine. 9% of protein is alanine. And so this guy here, right, that's the variable group of which there are 20. For alanine, that's a CH3 group. And then we have leucine, which is about 8% of protein is leucine. Valine, about 8% of protein is valine. Lysine, about 7%. So those are the five most abundant amino acids in protein. So notice that leucine, that's an essential amino acid. There's a lot of it in protein. It has to come from the diet. Valine, that's another essential amino acid. There's a lot of it in protein. That has to come from the diet. Lysine, this is another essential amino acid. There's a lot of it in protein. It has to all come from the diet. So of the five most common amino acids, 3 of them are essential. Right, so that's why you have to eat your protein. Okay, now let's talk about the least common, the rarest amino acids. Okay, coming in at only 3% is methionine. Only 3% of protein is methionine, and then tyrosine, only 3% there. Histidine, 2%. Cysteine, also 2%, and the rarest amino acid in protein is tryptophan. You've probably heard of tryptophan, right? In connection with the sleepiness that is provoked by that the Thanksgiving meal. Many people have heard of tryptophan, TRP. That's an amino acid. Only 1% of protein is composed of tryptophan. Okay, and what was essential over here? Essential. This one isn't, but this one is. So this is the only one that's not essential. That's the only one that your body can synthesize. So these very rare, these rarest amino acids, a lot of them have to come from the diet. Possibly that's why they're rare. I don't know. Maybe Mother Nature has engineered them in that way. Okay. So now let's talk about stereochemistry of the alpha amino acids. The alpha amino acids belong to one of 2 stereochemical families, just like the carbohydrates belong either to the D family or the L family. It's the very same for the proteins. I mean, for the amino acids. We have D amino acids and we have L amino acids. So they can be either D or L, right? Just like the carbohydrates. However, the rules for assigning D and L for an amino acid are pretty different from the rules of assigning D or L to a sugar. Um, I'll just give you the bottom line right here, which is the amino acid the alpha carbon of the amino acid is a chirality center, right? Because it's a steric number 4 and it's bonded to 4 different groups. So the alpha carbon of the amino acid is a chirality center, except if R is equal to H. Because if R is equal to H here, then it's not a chirality center. And this happens to be the most abundant amino acid, glycine, right? We just went through the relative abundances of the amino acids in protein. The most abundant amino acid in protein is glycine. It's the only amino acid that doesn't have a chirality center at the alpha carbon. And the bottom line is all amino acids coded for by DNA, right? I'm not talking about a Frankenstein monster lab creation, right? I'm talking about the naturally occurring amino acid that results from the translation of DNA into protein. All amino acids coded for by DNA have the S absolute configuration at the alpha carbon. And as such, they belong to the L stereochemical family. So we could talk about L-alanine and L-valine and whatever amino acid we're talking about. So all of the alpha amino acids have the S absolute configuration here, and they're called out. Oh, this chalk. But the truth is so messy. There is one exception. Except the amino acid cysteine, which is L, but R at the alpha carbon. Okay, so I want to explain why this is, but the take-home message here is that the naturally occurring amino acids coded for by DNA all have the S absolute configuration here, and they are called the L-alpha amino acids. The only exception is cysteine, which has the R absolute configuration, but it's still called L anyway, right? This is for historical reasons, because when they were figuring out what was D and what was L, this was in the beginning of early 1900s, where people didn't even all agree that stuff was made out of atoms. So it's just a historical hangover. Okay. So let me show you how the D and L family of amino acids is actually assigned. D and L are assigned from a Fisher projection. And that Fisher projection has to be drawn in a certain way and in no other way. The amino group would be pictured on the left. The chirality center is in the center here, and the carboxylic acid group is pictured on the right. Okay, so there's the Fisher projection. And when you draw the amino group on the left, the carboxylic acid group on the right, the alpha carbon here in the center, and when you put the H down here, the R is always up here on top, right? And remember, in a Fisher projection, the east-west bonds are reaching out to hug you, right? So if we did the determination of absolute configuration, we see nitrogen would be 1, the carboxylic acid group would be 2, hydrogen would be 4, and this guy is nearly always going to come in at number 3. So with this hydrogen pointing away from me, I see 1, 2, 3, that's the S absolute configuration. Okay, this would be the S absolute configuration, except for cysteine, right? But this is how the D and L family is assigned, is that for every amino acid coded for by protein, when you draw a Fisher projection and put the amino group on the left and the carboxylic acid group on the right and the hydrogen down, that variable substituent, that 1 of 20 substituent is always going to be at 12 o'clock for every amino acid coded for by DNA, whether it's cysteine or not. This usually works out to be the S absolute configuration, but not for cysteine. But, all right, so this is how we draw the Fisher projection for an amino acid. Cysteine looks like that. This is L, cysteine. But now let's determine the absolute configuration. Nitrogen's going to win. Hydrogen's going to lose. We go from the chirality center. We hit a carbon there. We hit a carbon there. We're tied. We have to look at the next set of atoms. Remember all of this from earlier in the semester? The next set of atoms here is OOO, where, remember, a double bond is deconstructed as an equivalent number of single bonds. Okay, the next set of atoms here is SHH. Well, sulfur beats an oxygen because sulfur has a higher atomic number than oxygen. So that for most of the amino acids, except for cysteine, for most of the amino acids, the carboxylic acid group always comes in at rank number 2. But for cysteine, the carboxylic acid group comes in at rank number 3, and this mercaptomethyl group comes in at number 2. Okay, and so now with this hydrogen pointing away from me, remember the east-west bonds are reaching out to hug you. This is 1, 2, 3, that's R. That's an R absolute configuration. So the way that the D and L is assigned is it's more complicated in a way than the assignment of D and L for a carbohydrate. It's all based on this Fisher projection. But remember that it's nearly always the S absolute configuration here, except for cysteine. L-cysteine has the R absolute configuration. Okay, so obviously one of the things that I would like for you to be able to do is to tell me whether I'm looking at a naturally occurring amino acid coded for by DNA, that would be the L alpha amino acid. Or if I'm looking at a Frankenstein monster lab creation, the D alpha amino acid, and also some insects and bacteria also have D amino acids, but not a human being. All right, so let's try maybe something like this. Maybe from a Fisher projection. Oh, I'm going to put the carboxylic acid down here. And maybe I'll put the NH2 group up here, hydrogen there, and CH3 there. This is alanine, but I would like for you to tell me, is this D-alanine that we're looking at here, or is it L-alanine? So why don't you take a few minutes and try to figure that out? So I want you to be able to identify whether it's a D or L amino acid, regardless of how it's drawn, right? Fisher projection, dash and wedge, whatever. 50-50 chance of being right just by guessing. All right, so nitrogen has the highest atomic number of all of the atoms bonded to the chirality center. And then the carboxylic acid carbon would be 2. Because this carbon and this carbon were tied, we have to look at the next set of atoms. This carbon is bonded to oxygen. This one's just bonded to hydrogen. So he's 3 and he's 4. He loses. The east-west bonds are reaching out to hug you. If I stand over here, this hydrogen is about to poke my eye out. It's looking at me. I'm going to note the sweep of the top 3 ranks and then reverse it for the right answer. 1 is in the back there somewhere. 2 is also in the back there somewhere. 3 is now reaching out to hug me if I'm standing over here. So that looks like a clockwise sweep. Reverse it for the right answer. This is an S absolute configuration. Is it cysteine? No. So that's the L-alanine. Okay, so what about something that, let's try dashing and wedging. Probably it's a lot easier. Okay, is that an alpha amino acid? Heck yes. There's the carboxylic acid carbon. There's the alpha carbon. An alpha amino acid has this amine nitrogen bonded to the alpha carbon. So this isn't NH2, but it is an amino group, right? This is an amino group as well. This is an amino group as well. This is the amino acid proline, PRO. And now I'd like for you to tell me whether I'm looking at the L proline or the D proline. So maybe dashing and wedging is easier than the Fisher projection. Is this L proline or is it D proline? So nitrogen is 1, carboxylic acid carbon is 2, this methylene down here, that's going to be 3, hydrogen is 4, and the hydrogen, the group of lowest rank, is facing away from me. The sweep is clockwise. This is D proline. So a human being doesn't have any D proline, right? This is something that we find only in some insects and in some bacteria and maybe in a laboratory created by an organic chemist. This is one of the great unsolved mysteries of biology, is why has Mother Nature selected the L stereochemical family for most living organisms and never the D stereochemical family? Why aren't D and L mixed up all together in protein? No one has any idea why this is. All right, so that's the stereochemistry of the alpha amino acids. All right, so now let's get into talking about something about reactions of the alpha amino acids. First of all, acid-base properties. Of the alpha amino acids. So most alpha amino acids have two ionizable groups. There are two groups in the alpha amino acid that you're going to find on that famous pKa table that we distributed earlier in the semester. And most alpha amino acids have two pKa values, one of them referring to the amine protons on the amino nitrogen, and the other one referring to the pKa's of the carboxylic acid proton. Some amino acids have more than two pKa values associated with them because of acidic protons in the side chain. Okay, so let's look at an example. This is a lot of this is just review of something that we did before. I go to that table that I showed you on the course website, that the table of alpha amino acids, and I look up alanine, right? Okay, and so that table says that the carboxylic, so this is alanine, right? This is alanine. That table says that this proton has a pKa of 2.34, and that table says that this proton here, one of these, this proton here, has a pKa of 9.69. Well, one of the things that we know that we can do with pKa values is that we can establish the dominant form of the amino acid at a given pH. And the pH of 7.4, that's the most important pH for us because that is physiological pH. That is the pH of your blood, of your saliva, inside of your body, pH of nearly everything except possibly your stomach contents after you've eaten a meal where it's flooded with hydrochloric acid. So let's go revisit that and let's draw the dominant form of the amino acid at a given pH. So this is all review, right? We've done all of this before. So there's our pH scale. We go from 0 to 14. And we know from our previous discussion that something very special is going to happen to the pK 2.34 proton at pH 2.34. So I'm just going to indicate that here. 2.34, something very special is going to happen at pH 2.34. I'm going to run out of room. It's too short, tiny, about 2.34. We know that something very special is going to happen to the pK 9.69 proton at pH 9.69. So I'm just going to put 9.69 here. And what we're really interested in, I guess, is what is happening at pH 7.4, which is the physiological pH, which is going to be there somewhere. Okay, and so what we know from previous is that is that as we raise the pH by adding base, these acidic protons begin falling off. So that between pH 0 and pH 2.34, the dominant form of alanine is going to be, it's going to have those 3 amino protons and positive charge on nitrogen, and the carboxylic acid proton is going to be on. These are the dominant forms. Okay, and then above pH 2.34, now most of the pK 2.34 protons are gone, so this H goes away. So in this regime here, the dominant form is going to have a negative charge on that oxygen atom, and then at pH 9.69, most or above pH 9.69, most of the pK 9.69 protons are gone. So in this regime over here, the dominant form of the amino acid is going to look like that. Okay, so this is all something that we've done before. This has earth-shaking consequences because you are here, right? You are here. And one of the things that you've heard me say a bazillion times is that you're 85% water. And water is very good at dissolving stuff, but it's best at dissolving charged stuff, ionic stuff, sodium plus ion and chloride minus ion. Water is good at dissolving stuff that has a charge, but it's not as great at dissolving stuff that is neutral. So that even though you're 85% water, you are not a puddle, because at the pH of your body, the amino acid and the proteins are neutral. We have a positive charge over here, a negative charge over here. The amino acid and most proteins at physiological pH are neutral, and water, of which you are 85%, isn't that great at dissolving stuff that is neutral. At low pH, the amino acid is a positive ion. At high pH, the amino acid is a negative ion. This is very soluble in water. This is very soluble in water because they have an overall charge. But where we live at physiological pH, the amino acid is near its minimum of solubility. That's why you're not, even though you're 85% water, that's why you're not a puddle. So this exercise here that we've done before has some earth-shaking consequences. Okay, so that was all review, but now I want to intensify the presentation here and show you this, present this data to you in a little bit more rigorous way. Okay, so in order to do that, we're going to have to erase all the stuff. And I'll redraw my structure of alanine up here with the associated pKa's. So this one was 2.19. This one was 9.67. That's the amino acid alanine. And so instead, so now what I want to show you is just a different plot that amplifies that whole stuff about the dominance. Okay, so once again, what I want to show is a pH scale down here. That's going to be the pH scale. And that's going to go from 0 to 14. And now I want a y-axis here, which is going to be concentration. And of course, something very special is going to happen. 2.19, no, that should be 2.34. Sorry about that. Something very special is going to happen at pH 2.34. We just went through all of that. And something very special is going to happen at pH 9.69. Just went through all of that. Okay, so I've marked out those pHs corresponding to the pKa's of the alanine. Okay, and so let's say that initially, let's say call this maybe 1 molar, right? 1 molar. Oh, and maybe here let's put 0.5 molar. And I'm going to carry up that line there. I'm going to carry up that line there. And so we're talking about, we just finished talking about dominant form. What does dominant mean? Mostly this, that, and the other form. But dominant does not mean exclusive. If I say that if I'm drawing a structure and say that's the dominant form, I don't mean that's the only thing in there. All I mean is most of the stuff in there looks like that. Okay, now by careful measurement, I can measure the concentration of this, that, and the other form of the amino acid. Okay, so at low pH, what's the dominant form? Dominant form would be this one, right? We just went through all of that. Okay, and so if I measure the concentration of this guy, the dominant form below pH 2.34, I get a curve that looks like this. See, it's dominant. Most of the amino acid is present in this form. So I'm going to call this guy, I'm going to call him Roman 1. Okay, so this guy here, that's the curve corresponding to Roman 1. Now, at high pH, basic pH, we saw that the dominant form at high pH is going to be this anionic form. I'm going to call him Roman 3. All right, and he's dominant above pH 9.69. But if I were to carefully measure the concentration of this guy here, I would get a curve that is kind of like the mirror image of this. There's very little of 3 at low pH. There's very little of 3 at low pH. And then it starts to go up, and now it becomes dominant above pH 9.69. So this is the concentration curve of 3. In between here, in the physiological region, we went through how the dominant form is this neutral species, right? I'm going to call him Roman 2. So actually, we have these three forms. Okay, and now when I measure the concentration of this guy, I get something that looks like this. It looks like this bell-shaped curve. And we see again what we mean by dominance is okay. So this is Roman to the neutral form. What we see by dominance is that most of the amino acid is structure 1 until it reaches pH 2.34, and then it's no longer dominant because now 2 is becoming dominant along this region, and then above pH 9.69, 3 is dominant, right? But dominant does not mean exclusive. So the concentration of these 3 forms of the amino acid vary. Okay, now this guy right here, where 2 tops out, exactly corresponds to a point where 1, the concentration of the positive charge guy, is equal to the concentration of the negative charge guy, and the dominant form at this point is neutral. So the top of this curve, and which sits right above where these 2 lines intersect, this pH right here is called, oh here, where to write this? This pH right here is called the isoelectric pH, or the isoelectric point. And it is the pH at which the sample of amino acid is neutral. The sample has no charge. The dominant form is neutral, and the concentration of +1 guy is exactly equal to the concentration of -1 guy, so that this whole sample is neutral, has no charge. And remember, you're 85% water. Water is good at dissolving ionic stuff. Water is good at dissolving stuff that has a charge. This isoelectric pH, this is the pH of minimum solubility in water, right? And this has earth-shaking consequences, right? This is why you're not a puddle. Okay, so we're going to leave this here for now, and next time we'll talk more about this isoelectric pH. But before we go, any questions about anything? Any questions about anything? You have a homework due this Friday, I believe, and we have a test next Friday. I'll be publishing a study guide. Any questions about anything? No? Okay. Well, have a good day. Bye-bye.